Hello students, welcome to Inside Physics. Today we are going to learn about refraction of light and Snell's law. So what is refraction? And before that we are going to see some points about light. So if light is considered as an electromagnetic transverse wave and the propagation of light direction is shown like this. See, for drawing the ray diagrams, we usually take the wave as a straight line so that it is easy to draw the ray diagrams, and this straight line in the direction of this electromagnetic light wave is called a ray. So here ray optics is the study of light based on the ray diagrams, and here the wave picture is considered for the study of properties like refraction and reflection. So here we are going to see the concept of refraction. So what is the concept of refraction means? See, whenever the light is entering from one medium to another medium with different refractive indices, then it changes its direction of propagation from its rectilinear path. So this is called refraction. That means the light literally bends whenever it is passing through one medium to another medium. We can see a lot of examples in our daily life. In our window, the light will pass through the glasses of the window and it comes from the sun to the nearest to our place. Here also the light in our daily life passes through different mediums like glasses, liquids, gases, and the light from the sun obviously comes through the atmospheric gases and it also refracts there. So here if you consider any interface is the medium between two mediums, here the border between any two mediums, and if the light is incident on the border of the two mediums, say it is a rarer medium or denser medium or denser to rarer. So here the mediums of different kind will have different densities. Those are called the optical density of a medium. So optical density is different from normal mass density. Normally we know that the mass density D is equal to mass per unit volume for a particular material. But here the optical density is the ratio of speed of light in different mediums. So if we consider this is the medium 1, this is medium 2. See, if we say this is rarer medium, that means it is optically rarer. If say this is denser medium, this is optically denser. So normal density should not be confused with optical density. For example, you take turpentine and water. Turpentine is the mass density of turpentine is less than the water, but the optical density of turpentine is more than the water. Here, so there may be a less dense objects, but their optical density may be high. Here also, we will see an example and find out what are the laws of refraction. Here, whenever there is an interface is nothing but border of two mediums. There is an incident ray and this is the normal drawn to the interface. There are two kinds of reflection and refraction happens at the point of incidence. Say P is the point of incidence where the incident light is touching the border of these two mediums. This is written as interface. And some part of light will be reflected back into the same medium and the other part will be passing through the second medium by changing its direction depending on the optical density of two mediums. So if it is passing from rarer medium to denser medium, the light ray will be bending towards the normal. This is the normal. Normal means perpendicular to the interface. This is called a normal. And this is angle of incidence, as we all know, and this is angle of reflection, and this is angle of refraction. So all the angles are determined with the help of this normal. The angle between the incident ray and the normal is called angle of incidence I. The angle between the reflected ray and normal is called reflecting angle or angle of reflection. So in the same way, this is refraction angle or angle of refraction. So here some part of light is reflected and the other will be passing through to the other medium. So here if you observe, normally if it is not deviated, the light ray would pass through the same rectilinear path like this, but you can observe that it has bent towards the normal. Why? Because in the optically denser mediums, the speed of light will be changing. That means the speed will decrease. So in this sense, we will consider it may travel a lesser distance by reducing its speed. So the direction is changed and it is bent towards the normal. If you consider in reverse, suppose say this is denser to rarer. We consider this is moving from denser to rarer. So in this way, the incident ray will refract into the second medium by bending away from the normal. I will show this in this diagram. So this is the normal and the light ray will be bending away from the normal. Why? Because the optical density of the second medium is less than the first medium, and this is the refracting angle. Okay. So these are the kind of rules that we can understand from the refraction, and here the normal and the refracted ray, the point of incidence and the incident ray. So if we close this reflecting ray, because now we are studying the refraction part and we are not concerned anymore with the reflected ray. The first rule of refraction is the incident ray, normal and point of incidence and the refracted ray, all the four must lie in the same plane. So all those four which I have told you, incident ray, normal, point of incidence, refracted ray, must lie in the same plane. This is the first refraction rule, and these rules are identified by the scientist called Snell. While on his observations and experiments on light, that's why we always call the refraction is followed by the Snell's law. So Snell is a scientist who done a lot of experiments on light and found out some refraction principles, which is the first one is all the four of these must lie in the same plane, and the second one, the ratio of sine of angle of incidence to the sine of angle of refraction is equal to refractive index. That is the second principle. We can write as sine of I by sine or sine of angle of incidence to the ratio of sine of angle of refraction is nothing but ratio of the refractive index of second medium to the first medium. N2 by, you can write it as N1 this is considered to be the refractive index mu. Refractive index is nothing but it is defined as the speed of light in the air to the speed of light in the mediums. Refractive index is the ratio of speed of light in air, that is C naught, to speed of light in any other medium. That is the definition of refractive index. That means we are considering the speed of light and we are comparing it with the other medium. For example, say the refractive index is 1.33 for water and speed of light in water is Cw. We can write it as C naught by Cw. We always know speed of light in air is 3 into 10 to the power of 8 meters per second. So in this way, substituting the C naught value, we can find the speed of light in water. This is an example how we understand the refractive index of a particular medium. Here by Snell's law, sin I by sin r is equal to ratio of the refractive index of second medium to first medium. Here we have written n to 1. That means the light is propagating from first medium to second medium. Okay. So if if the angle of incidence is 0, this becomes 0, and if the angle of refraction is say 90 degrees at a critical angle, the refracting angle will become 90 degrees. So this incidence angle will become critical angle at if the angle of refraction is passing, the refracted ray passing through the interface. So these are the some of the points. Then we can write this as sin IC is equal to sin IC by this sin R where the refracted ray goes along the border at a critical angle. This becomes sin 90 becomes 1. Then this is nothing but the refractive index of the medium. So this is how we all understand the concept of refraction. Now generally we observe the refraction through some glasses, and we also consider the refraction when it is entering into some thick transparent materials. So in that way, this is a process of observation in our daily life. So we will see what is lateral shift now. Lateral shift. See, when we take a thick glass slab like this, the light is entering into the glass slab with some angle obliquely with some oblique incidence. So say this is angle of incidence I1, and this is the normal drawn to the border of two mediums. Say this is air to glass medium. The light ray is going from air to glass. So in this way the ray will bend towards the normal. Okay. So here again I am drawing the normal to the interface, and this is angle of incidence 2. You can consider this. Again two refractions will happen. Here this is angle of incidence 2. This is angle of refraction 1. And again here it is going from denser to rarer. So this is a glass slab and higher optical density, and the refracted ray will obviously go away from the normal. Okay, so if you observe, if the glass slab is not here, the incident light ray will be passing through the same rectilinear path without any deviation, like this. But after entering into the glass plate, it has undergone the refraction at two interfaces, and this is called angle of refraction 2. So if you observe this, these two rays are parallel, and there is a shift of the light from this rectilinear path to the other side. So this is a shift. The light is shifted in this direction, and the distance between this is called the lateral shift. So here what we are understanding, lateral shift. So this is the lateral shift. When the light is entering from one medium to another medium, it actually deviates from its original path. So we can understand the refraction with these kind of examples. Okay, so whenever we are taking the ratio of refractive indices of two media, we can write the ratios in this way also. Say the light is entering from second medium to third medium, so the ratio will be n3 by n2, and this can be written as n3 by n1 into n1 by n2. So here that means n31 into n12. So the light entering from first medium to third medium here, and the second medium to first medium. So in this way we can also consider if there are more than two mediums, the light will be entering from 1 to 2, 2 to 3, and so on, like that. So this can be understood with the ratios of their refractive indices. The ratio of speed of light in two different media gives the optical density of the medium. So this is the concept, and we will see the observations in our daily life, what the refraction will make and how they look like. We are all observing in our daily life. There are some observations like apparent depth. So when we take a beaker of some liquid, say water, with refractive index 1.33. So generally if you observe the water from the above, you will see that the bottom of the beaker, this say is a glass beaker of water. So here see, the bottom we are observing will appear to be raised to some height. It is not actually raised, but it appears to be raised to some height. If you are observing from here, this is your eye, human eye, and the light from this bottom will be passing through the water like this to reach your eye. And here if you draw the normal to the surface of two mediums, the light is passing from denser medium to rarer medium, so that it will bend away from the normal. So like this, right? If this is the interface, this is the interface of two medium, and we are drawing two normals to understand the refraction. This is the light coming from the bottom of the beaker. The light rays can be seen from this observer, and actually if you observe the refracted rays, they will meet at a point which is higher than the actual depth. So they are actually meeting here. this is a point, the original point, and they actually refracted rays met at this point. So we observe the lower level, this bottom level of the beaker to be little bit raised, and this is because of the refraction of light passing through one medium to another, and this is called the apparent height of the object or bottom level, and this is the real apparent height, this is the real height. Okay, so we can get the refractive index by considering the apparent depth and real depth. Okay, so we can also say this as considered to be the apparent depth, this one from here to here. So the depth is always measured from the top surface, this is the surface level, and the depth is always measured into the deep section and it touches the bottom level. So from here to here, this is called the real depth. This is called the real depth. Here the real depth by apparent depth, that means the refractive index of this medium is given by real depth by apparent depth. So this is the refractive index of the medium. So this is how we see the daily observations, and we can understand the concept of refraction. Now we see one more example and we will conclude this session of refraction. We generally observe the sunset and sunrise while observing from our earth. So if you consider the earth, and this is the atmosphere around the earth. We all know that there is an atmospheric layers around the earth, and see, while the sun rise, actually we observe that the sunrise observed actually before the actual sunrise, right? So we take the sun position here, and if you observe from here, from the earth, this line of observation is called horizon. When you observe this from the earth, the line of observation is called horizon, and the actual position of the sun may be here, okay, before sunrise. So we will see the sunrise actually the little bit before the actual sunrise. See, the light coming from this sun, the actual position, like this onto this atmospheric layers, onto these atmospheric layers. Okay, so when you draw the normal to this surface again, this light is entering from optically lighter denser to higher denser. So that means rarer medium to denser medium. So it obviously bends towards the normal. So we need to consider this ray incidenting nearer to the observer, then we can feel the diagram better. So this is the incident ray, this you may consider the normal, and this is bending towards the normal. So here bending towards the normal. Then if you observe this we may change the diagram to a better position, so that here it is incidenting here. This is the normal, so this is bend towards the observer. So this ray actually is indicating the sun at a higher position. So we have taken 2 or 3 steps to draw the correct picture. So this is the refracted ray, this is the incident ray, this is the normal. So if you observe, the refracted ray is actually observed by this observer, and the sun appears to be above the horizon, even though it is not actually crossed the horizon. So we observe the sunrise little bit before the time of the time lapse is 2 minutes. The time lapse between the observed sunrise and the actual sunrise is 2 minutes. In the same way, while the sun is setting down, that means at the time of sunset, see, the sun has actually gone down as we observe in the sunset, but due to this refraction of light, the sun appears still to be there above the horizon, even though he has already set down the horizon and actually disappeared from the observation of the observer. But due to this refraction and bending of light, the sun appears to be still above the horizon, still is about to set, the sunset still about to happen. So there is always, the sunset is after the actual sunset, and the sunrise is before the actual sunrise. So this is how we see, and the time lapse I already told is 2 minutes, and almost it if you consider this in degrees, it will be around 0.1 degrees, and the difference is 2 minutes. Okay, so here we will conclude this session with the full concept of refraction. I hope you understood the concept, and if you have anything to say or comment, you can put in the comment box, so that I can explain whatever the doubts you have. Okay.